All right, so this problem says in nuclear fission, a nucleus splits roughly in half. What is the potential 2 times 10 to the minus 14 meters from a fragment that has 46 protons in it? Okay. So in nuclear fission, essentially you're taking neutrons and shooting them at U-235. This thing splits into 2 pieces and you get 3 neutrons. And the way you get energy is these products weigh less than these guys. Anytime the products weigh less than this, the missing mass is converted to energy. Okay, and now when they split into 2 pieces, roughly, okay, so this has a mass of 235 units. Roughly, this guy has these 2 pieces are centered around 90 units and 120 units, roughly. Okay. Every time they don't break up the same way, they break up different ways. But anyway, these 2 pieces, roughly 90 units and 90 mass units and 120 mass units. Anyway, okay. So what we are saying is, do you guys remember what is the size of a nucleus? 10 to the negative 15 meters. Okay, so now they've split up and they are 10 to the negative 14 meters apart. So roughly 10 times their size. If they were as big as your fist, they're 10 times the distance apart. And now what is their potential energy? Okay. What is the potential energy? What is the potential 2.2 times 10 to the minus 14 meters from the fragment? And then what is the potential energy of a similar charged fragment? Okay, so we'll find that. So for part A, here's the fragment, and you're finding the potential at a distance of 2 times 10 to the minus 14 meters. And the potential at that location is given by KQ by R. And that's equal to K is 9 times 10 to the 9 Newton meter square, Coulomb square. The charge is 46 E, 46 times the charge of an electron, divided by the distance 2 into 10 minus 14 meters. So that's the potential at that location. Okay. And I'll just, so the potential at that location is, so let's take your powers of 10. You get 10 minus 5, and then, so that leaves 10 to the 4. 10 to the 4 volts. 9 times 46 times 1.6 divided by 2. Okay, so what we are saying is essentially here's a nucleus, and if you're 10 times the size of the nucleus away, the voltage there is still 3 million volts. That's what we just calculated. Yeah. Now, in part B, we'll calculate what is the potential energy of these 2 guys. They're both positively charged, and so the potential energy and that potential energy would be converted to kinetic energy as they're flying apart. Okay. All right, so let's do the potential energy, part B. The potential energy of 2 fragments, oops. So here are the 2 fragments. They're both positively charged. 46 E, 46. Is it 46 or 48? 46. Okay. And actually, so let me simplify this. So Q times V. Remember this was V, so Q2 times V, which is 46E times V. And the voltage was 3.31 into 10 minus 10 to the 6 volts. And this works out to that's 10 minus 13, 10 minus 13, and you get, so it works out to 24.4 into 10 minus 12 joules. That is the potential energy of those two fragments. Okay. The potential energy of the pair. And again, so these fly apart, gets converted to kinetic energy, so that, and that's, they heat the surrounding fluid. And what do you do with that heat? You take that heat, boil water, produce steam, and the steam turns a turbine. Okay? And we'll learn about that, how to produce electricity. All right. Do you guys need a break?